In late October 2025, astronomers recorded something that no telescope had ever captured before, a radio signature from an interstellar visitor known as 3I Atlas. The discovery, confirmed on October 24 by South Africa's MeerKAT array, revealed two faint but precise absorption lines at 1665 and 1667 MHz, the hallmark frequencies of hydroxyl radicals produced when water molecules break apart under ultraviolet light. It was chemistry, not communication, yet it marked the first time humanity had detected the molecular fingerprints of an object born beyond the solar system. The finding arrived almost by accident. MeerKAT's 64 dishes had been aimed toward a patch of sky less than 4 degrees from the sun, an area astronomers rarely attempt to observe because the sun's radio glare overwhelms weaker signals. On that dark morning in the Karoo Desert, however, geometry and timing aligned. 3I Atlas was racing through the inner solar system at roughly -5.6 kilometers per second relative to Earth, a motion that Doppler shifted its radio signature just far enough from the sun's background noise for the array to isolate it. Within hours, the data were verified, cross-checked for satellite interference, and confirmed by multiple scans. What emerged from the noise was a clear imprint of water chemistry unfolding hundreds of millions of kilometers away. This detection was remarkable for another reason. It came from the same general region of the sky as the famous WOW signal of 1977, a narrowband radio burst that has never been explained. The coincidence, about 9 degrees of separation on the celestial sphere, sparked immediate comparisons. Yet scientists were quick to clarify that the new finding was an absorption phenomenon, not an intentional transmission. Still, the echo of history reminded the community how easily curiosity and speculation can intertwine when the universe presents something unfamiliar. 3I Atlas had already intrigued astronomers since its discovery in July 2025 by the Atlas Survey. It was only the third confirmed interstellar object after 1I/Oumuamua, 2017, and 2I/Borisov, 2019. Unlike its predecessors, Atlas combined characteristics of both, a cometary coma like Borisov's but odd variations in brightness and tail geometry that hinted at something less straightforward. As it approached the sun, the object warmed to about 230 Kelvin, 43 degrees C, just enough for water ice on its surface to sublimate directly into vapor. That vapor formed a thin atmosphere or coma around the nucleus. Ultraviolet radiation split the water molecules, producing hydroxyl radicals that absorbed radio light at precisely the frequencies MeerKAT detected. In essence, astronomers were listening to interstellar water boiling off an ancient iceberg. The hydroxyl signature itself was not exotic. Comets in our own solar system display it routinely, and for decades scientists have used these lines to estimate a comet's water content. What made this case historic was the source's origin. For the first time, Earth's instruments were analyzing the chemical composition of material forged around another star without the aid of a spacecraft. The data showed that the same physics and chemistry governing our comets operate elsewhere, reinforcing the idea that the ingredients of life are common across the galaxy. As measurements accumulated, subtle anomalies emerged. Observers noted that Atlas developed both a conventional tail pointing away from the sun and an anti-tail apparently directed toward it, an effect that can arise from perspective but rarely with such symmetry. Its brightness fluctuated by about half a magnitude over days, suggesting irregular jets of gas or an elongated, fast-spinning nucleus. Some jets seemed to erupt from regions not illuminated by sunlight, implying subsurface heating or complex layering of ices. None of these behaviors violated physics, yet together they portrayed a body more intricate than a simple lump of frozen water. The proximity of Atlas's trajectory to the WOW signal's coordinates reignited long-dormant debates about extraterrestrial communication. The 1977 event, a 72-second burst near 1420 MHz, close to the hydrogen line, remains one of astronomy's enduring puzzles. Nearly half a century later, another unexplained radio phenomenon appeared from roughly the same part of the sky. The resemblance was enough for SETI enthusiasts to wonder aloud, though professional astronomers maintained restraint. Every test of the Atlas data pointed to ordinary chemistry amplified by extraordinary timing. Timing indeed was everything. Earlier attempts to observe the object on September 20 and 28 had produced nothing. In those weeks, Atlas was still too cold for water to sublimate. By October 24, it was days from perihelion, the closest point to the sun, when the heating rate and geometry aligned perfectly. Had MeerKAT looked 2 days later, the comet would have been lost in the sun's glare. The detection window lasted only hours, a cosmic blink that underscored how much luck accompanies discovery. For scientists, luck is useful only when paired with rigorous analysis. The data were run through interference filters, checked against satellite catalogs, and compared with theoretical line shapes. The widths of the absorption features matched velocities expected from molecules expanding out of a small nucleus. Their stability across scans confirmed that the signal tracked the object's motion precisely. The conclusion was unavoidable. The hydroxyl lines were real, and they originated from 3I Atlas. Once the excitement settled, the deeper meaning came into focus. If interstellar comets carry water and organic molecules, then the galaxy is constantly exchanging the raw materials of life. Planetary systems eject debris during their formation. Some of those icy fragments travel for millions of years before wandering into another star's domain. When they do, they can deliver volatile compounds to young planets, a mechanism long proposed to explain how Earth acquired its oceans. Atlas's chemistry provided direct evidence that such transfer is possible across interstellar distances. The discovery also prompted a reassessment of how rare these visitors truly are. Statistical models suggest that at any given moment dozens of interstellar bodies pass through the inner solar system, most too small or faint to detect. That we have confirmed only 3 in 8 years speaks more to the limitations of our surveys than to cosmic scarcity. Future wide-field telescopes and continuous radio monitoring may reveal a steady traffic of alien debris, each piece carrying a different story about the planetary system that expelled it. Inevitably, speculation about artificial origins followed. Some commentators wondered whether Atlas's symmetrical tails or slight trajectory deviations signaled control, perhaps a probe disguised as a comet, maneuvering via directed outgassing. The idea is imaginative but unnecessary. Non-gravitational forces from uneven sublimation are well documented. Even Halley's Comet experiences measurable thrust from jets of vapor. The deviations observed in Atlas fall squarely within those bounds. To propose propulsion requires evidence far stronger than small changes explainable by physics. Still, the conversation illustrates how thin the line can be between scientific curiosity and the human desire for drama. More fruitful than conjecture is what Atlas teaches about cometary physics. At 230 Kelvin, water sublimation is vigorous, but more volatile ices such as carbon monoxide and methane would have escaped long ago during the object's journey through interstellar space. What remains is a cleaned nucleus dominated by water ice and refractory organics, a time capsule of primordial material. Modeling its outgassing helps scientists estimate how ices evolve in the harsh radiation of deep space and how long they can survive between stars. The conclusion is optimistic. Volatile-rich bodies can persist for millions of years, preserving complex chemistry until a passing star rekindles their activity. That endurance has profound implications for astrobiology. Laboratory experiments have shown that simple organic molecules can form in irradiated ices composed of water, methanol, and ammonia, conditions common in comets. Amino acids like glycine emerge spontaneously when such ices are warmed. If comets throughout the galaxy undergo the same chemistry, then every stellar system may seed its neighbors with prebiotic material. Life, or at least its ingredients, becomes a shared enterprise of the cosmos rather than a local accident. The MeerKAT detection also marks a turning point for radio astronomy itself. For decades, instruments like Green Bank, FAST in China, and the Very Large Array have hunted for narrowband beacons, signals intentionally broadcast by intelligent civilizations. None have been found. The Atlas event demonstrates another path, the study of non-intentional technosignatures, or more broadly, of any measurable trace of activity, natural or artificial, that carries information about processes elsewhere. A civilization manipulating comets or atmospheres would leave chemical fingerprints, just as industry leaves spectral traces on Earth. Even without deliberate messaging, technology alters environments in ways spectroscopy can detect. The line between biology, chemistry, and engineering may be finer than we think. In that sense, 3I Atlas represents more than a single observation. It is a proof of concept for a new kind of cosmic listening. By capturing how sunlight fractures molecules on a body from another star, scientists have shown that radio telescopes can perform chemical forensics across interstellar space. Future arrays with greater sensitivity could map the molecular inventories of dozens of such travelers, revealing whether their ices share isotopic ratios with ours or display signatures of unfamiliar chemistry. Each detection will add another data point to the emerging map of galactic exchange. What we know so far is both humbling and exhilarating. The same water that sustains life on Earth exists frozen in countless wanderers adrift between stars. The same physics that governs a comet's shimmer in our night sky governs their passage in distant systems. And sometimes, when geometry and chance align, that shared chemistry whispers across the void in a language we can finally understand. No message, no code, just molecules absorbing light at precise frequencies, reminding us that life's essential ingredients are written everywhere. The excitement surrounding Atlas will fade as it recedes into darkness, moving at more than 40 kilometers per second toward the outer regions of the solar system. Yet its brief appearance has expanded humanity's senses. We now know that radio telescopes can detect the breath of an alien comet, that the boundaries of our solar system are porous to the chemistry of distant suns, and that listening to the universe need not mean waiting for a call. It can mean recognizing the conversation already in progress. In the months since the discovery, other observatories have joined the search, scanning for new interstellar arrivals and re-examining old data for overlooked signals. None may reproduce the conditions of that October morning, but each attempt refines our understanding of how to hear such faint cosmic murmurs. The story of 3I Atlas is therefore less about a single anomaly than about the growing precision of human perception. It is a reminder that the universe communicates constantly through physics itself, and that comprehension begins not with speculation, but with the disciplined act of paying attention.